So we have Giovanni Galli. He obtained his master's degree from the University of Bologna in 2015 with Professor Eva Picardi. And he's currently, as he said, a PhD candidate at the University of Urbino, a research methods in science and technology program. His research interests are connected to the epistemology of big data, scientific realism, and scientific understanding. He's also interested in the scientific communication, and as a local administrator, he also focuses on the role of science, on the role sciences play for policy making processes. And he's going to talk on scientific understanding in the big data era. I'm looking forward to hear that.
Thank you very much. It's really a pleasure to take part to this symposium, and I'm looking forward to all the contributions to this symposium. I will give you today an overview of the issues concerning the theory of scientific understanding in what we can call the big data era. And I can
Giovanni, I think if you press the presentation mode, it will come up full screen a little bit. That's unless I'm seeing something different to everybody else.
Can you can't you see my presentation now?
We just need to, if you click on the presentation mode at the top, it should come up and fill the full screen. So across the top, when you have the so not on Zoom, on the PowerPoint itself. It's not the end of the world. It just looks nicer on the videos, right? And that's what we're all here for.
Can you see now the presentation full mode?
No, you stopped sharing your screen.
Yeah.
Oh, well, wait a moment. Okay.
Yeah, and then if you go along the top, you'll see there's right up to the top of the red bit of your PowerPoint, and there's a sort of a screen with an arrow on it. So you've got one arrow pointing to the left, one arrow pointing to the right.
So and now you can see the first one, the first slide.
Yes, but we
now
can
the second slide.
Yeah, that's great.
Okay, it's okay. It's like that, or so I can go on.
Yes, I guess you can. We were just talking about like making it full screen. So you press F5 or you just go on, that would be no problem.
Wait a moment. Yeah, F5 doesn't work. Okay.
There you go. Yeah. Just press
here. Okay, sorry.
Yes, perfect.
So first of all, I'll give a definition of big data, and then I'll introduce two main alternative ways to conceive data before entering in the issues concerning the epistemology of big data and describing some conceptions of scientific understanding. At the end, I'll address two arguments against scientific realism in order to state that scientific realism and serendipitous discoveries have still a place in scientific research carried through big data technologies. So while we are doing the symposium, a huge amount of data are produced. 1.7 megabyte of data is created every second by every person in 2020. And only in the last 2 years, we produced the 90% of data in the world. Every day, humans produce 2.5 quintillion bytes. That means that in 2025, humans will generate daily 463 exabytes. We estimate that in 2020, we'll produce 40 zettabytes. So it's 40 times 10 power 21 bytes. So big data revolution has become a common idea in the last years, and its implication is that algorithm will predict everything. But is it the case? Sciences and application make use indeed of big data technologies, and physics, astrophysics, economy, social sciences, biology, geology, and others can be called now data-centric sciences, because producing and manipulating huge amount of data is a practice we can detect in many sciences. And there are structured and unstructured data. The former are well-defined and searchable types of data, and the latter are data stored in its native format. We can distinguish many features of data, the so-called many V's of data, such as volume, variety, velocity, veracity, and the value, the ability to transform amounts of data into knowledge, into business, into discoveries. So considering these pictures, do science, do theory making, do serendipity have still a place, or all is predictable and no more theory is needed? So we need then a big data analysis framework to account for data-centric sciences. Well, I guess that all of you watched Perseverance landing on Mars on 8th February. Well, our Mars, so the planet we must analyze, is the family of data-centric sciences. But you know, Perseverance had a host, which is the Ingenuity helicopter, and Mimi Ong is the project manager at the JLP that worked on Ingenuity. NASA facts about Mars helicopter reveal an important insight about the relation between science and data. But first of all, we must distinguish between data generated by scientific and technological research from data generated by users' interaction on a media platform and with Internet of Things. Well, I'm interested here with the former type of data. About the scientific technological data, I must distinguish them between data generated for technological purposes and data relevant to scientific research. Ingenuity, as NASA facts say, is solely a demonstration of technology, while Mars 2020 Perseverance mission is searching for signs, so samples of data of ancient life. Both types of data are relevant for our purpose of developing a theory of scientific data-centric understanding. So what are data? We have mainly two views regarding the definition of data, the representational view and the relational view. According to the representational view, data are reliable representations of reality, which are produced via the interaction between humans and the world. According to the representative approach, data are objects with a fixed and unchangeable content, whose meaning, in virtue of being representations of reality, needs to be investigated and revealed step by step through adequate inferential methods. And the relational view, the alternative view, says that data are objects that are treated as potential or actual evidence for scientific claims in ways that can, at least in principle, be scrutinized and accounted for. So the meaning assigned to data depends on their provenance, on their physical features, on what these features are taken to represent, and on the motivation and instruments used to visualize them and to defend specific interpretation. The reliability of data thus depends on the credibility and strictness of the processes used to produce and analyze them. And this is the view proposed by Sabina Leonelli. So given the definition of data by Leonelli, we can throw important insight about the features of data in data-centric scientific activities. So Leonelli says, I conceptualize data as tool for communication, whose main function is to enable intellectual and material exchanges across individuals, collectives, cultures, nations. I will also insist that data are material artifacts whose concrete characteristics, including their format and the medium through which they are conveyed, are as relevant to understanding their epistemic role as their social and conceptual functions. So data are, yes, what is given by definition, but they are given while they are made. And we must care about the epistemic value of data in their making, production, and use. Data are situated, and it is important to follow them through the journeys from platform to platform, institution to institution, lab to lab, scientist to scientist. Their journey can also give us insight about their logical structure. Big data technologies make the logical structures of data even more complex. And today, the concepts of inductive inference, probability, uncertainty, and forecasting are acquiring even more importance. And that is why it is urgent to develop an epistemology of big data and data-centric sciences. So 5 are the main risks we encounter in analyzing the epistemic value of big data. The first one is conservatism. It is the problem of old data. When researchers use old data to reduce costs, they come back to analyze old data. And the risk is to develop research which is conservative and not very much creative. And the risk is to maximize what we already know about the natural world, despite the exploration of new ways of inquiry and raising complexity. The second problem is the unreliability, and it is the problem of unreliable data. Once we consider the conditions of data mobilization, it is difficult to assess their value. Some infrastructures have no filter to differentiate reliable data from the unreliable ones. And the risk here is to build a huge big data, a paper castle, matching together a huge amount of data, regardless to the differences about their reliability as knowledge sources. The third problem is about mystification, and this is the problem of partial data. Users of big data may forget that what they are manipulating is not a complete sample of the reality, but it is rather a selection of reality made for practical limits and conceptual reasons. We must criticize the idea that big data are a complete representation of reality, because this illusion is hacking the critical thinking abilities with which researchers deal with analysis and interpretation of empirical data. And the problem of corruption is the problem of dishonest data. Data are also used not only as evidence for knowledge and scientific claims, but also as commercial goods. And organizations who can collect and analyze big data have economic and political power. And there is much ambiguity about the public or private status of data. For example, Niccolò Tempini showed how personal data on Facebook and Twitter are used both as scientific data and commercial goods. To this extent, the commodification of data is a risk because it implies that data are taken away from their original context and reused in a corrupted way. The last problem is the social damage. It's about the sensitive data. So we must say that there is not a clear distinction between the scientific conduct and the ethical conduct in the case of big data. One example for this problem is the Cambridge Analytica case, so represented by data that serve to characterize features of individual or cluster of individuals for business purposes, but without any deontology behind. So during the scientific activity, the main focus is on the scientific activity and research, scientists try to give explanations of phenomena. We can see explanation as the output of scientific activity, which is directed to the scientific understanding of phenomena under scrutiny. And there are different models of scientific understanding. The first one is the nomological and unificationist model, according to which scientific theories provide understanding by unifying the phenomena. So taken many phenomena scientists want to analyze, scientific theories provide understanding of them by unification in order to state the natural laws governing them. Another model is the causal and mechanistic model, according to which science gives understanding of the world by uncovering its causal structure. If we want to understand empirical phenomena, we must uncover their mechanism by their causal structures. There is another model which depicts scientific understanding, and it is proposed by Direct. While the first one was proposed by authors like Hempel, Friedman, Kitcher, and the second by authors Scriven and Salmon. So according to Direct, we can have a contextual model, CM, according to which the aims of science require intelligible theories. And Direct argue for this claim, saying that providing correct explanations is an epistemic aim of science, and correct explanation requires scientists to use intelligible theories. So given these two premises, the conclusion is that the epistemic aims of science require intelligible theories. It is to be noted that we use theory when we exercise the judgment, according to Direct, and skills that are needed to construct explanatory models of the phenomena. Direct gives a definition of the intelligibility science, since it is the crucial concept of his view. The value that, and the definition is that intelligibility is the value that scientists attribute to the cluster of qualities of a theory that facilitate the use of a theory. And in support of this view, he gives two criteria. One is the criterion for intelligibility of theories, and the other one is the criterion of understanding phenomena. According to the first criterion, a scientific theory, T, is intelligible for scientists if they can recognize the qualitatively characteristic consequences of T without performing exact calculation. And according to the criterion of understanding phenomena, a phenomenon P is understood scientifically if and only if there is an explanation of P that is based on an intelligible theory T and conforms to the basic epistemic values of empirical adequacy and internal consistency. But I have some concerns about the contextual model of Direct, and it is not well defined within this model what an epistemic aim is, neither are well defined the concepts of empirical adequacy and consistency. I am interested in what actually we miss in this picture. And I think that we miss in this picture the criterion for understanding data. Data features are important indeed to develop a theory of data-centric scientific understanding. And I think also that to develop it, we do not need a unique model of scientific understanding. Moreover, the contextual model is not committed to realist conception of scientific theories and models, but I think that if theories and models are successful also in data-centric sciences, the reason is that they are at least partially true. We now come back to detail the theory and data relation. And we consider two main arguments against scientific realism. So the underdetermination of theory and the novel prediction argument. We know that theories are always underdetermined by experimental data. It means that taken a certain domain of objects, of data, they do not impose a solely unique theory. That is why we cannot be certain to state what is the correct theory between all the relevant alternatives. Here we can see a good and elegant way to represent the underdetermination argument given by Mario Alai. So from a logical point of view, for any body of empirical data, however wide, it is possible to find infinitely many incompatible theories entailing them. Hence, at any time, there are infinitely many possible theories having the same class of empirical consequences. But the confirmation of a theory depends only on the class of its empirical consequences. Hence, all of those theories enjoy the same confirmation, and therefore, we cannot have reasons to believe that one of them, if any, is partially true to the exclusion to the others. I think we can find at least 3 arguments against underdetermination. One is that it is possible that the starting set of data can be explained by many hypotheses. Each one, yes, is incompatible, but which are empirically equivalent. And the second counter-argument is that 2 theories at a certain time could be empirically equivalent, but that won't be always the case, since every theory is tested with evidence through auxiliary hypotheses. Adding new hypotheses can further empirical consequences that can differentiate them. But I want to propose also a third way to deflate underdetermination argument, and this is a counter-argument based on the underdetermination of data itself. The starting point is the claim that making theories require making data. And let's take an example from Wiley in the area of paleontology. So according to Wiley, vertebrate fossils provide us a particularly clear instances of the underdetermination of potential data. There are many possible ways for a fossil to look as a result of a collection and preparation, she said. And just as there are many possible theories to explain that fossils' phylogeny, behavior, and role in its ecosystem. And scientists generally deal with the underdetermination of evidence by standardizing how evidence is prepared to argue that all specimens, all samples, all observations, and other traces processed by the same methods are comparable and valid. But it is not the case of vertebrate paleontology. In this case, we do not have standardized methods for preparing specimens. And I think that it is also the case for other scientific areas of inquiry, like gravity waves detection, microbes detection, and also human behavior studies. We have 3 moments in the underdetermination argument. The one is that of the theory. The other one is that of the data that scientists choose to serve as evidence for that theory. And the third one is the potential data that scientists could cite as evidence, but haven't yet. So it might appear that underdetermination weakens theory and data, theory and evidence, both of them, because it requires the theory and data to be the results of decisions and arguments rather than facts. But, however, if we recognize the value of evidence that applies to multiple theories with regards, for example, to open access datasets, we can avoid these risks. In that case, citing Leonelli, Sabina, underdetermination is a strength of scientific research, and that produced with high efforts and costs can and arguably should be used as evidence for a variety of claims about phenomena. So what about the other argument, the novel prediction argument? I must make a premise here. According to some authors like Napoletani, Panza, and Struppa, big data technologies, machine learning, deep learning, lead to what they call agnostic science. And it is a moderate position towards the end of theory. And they claim that data-centric sciences cannot produce a scientific understanding of phenomena because all the relevant inferences result opaque, results obscure. And they conclude that big data technologies are useful to solve problems, but they are not useful for scientific aims to understand phenomena. I think it is not the case, and the novel prediction arguments will say why. In philosophy of science, anti-realists point out that many theories historically were successful, but yet false. Theory success can be explained also by its predictive power. Well, yes, anti-realists say that theories have not a novel predictive power because theories about known phenomena are results of accommodation of phenomena. So scientists have just to accommodate the phenomena to make them suitable for the theory they want. But a piece of reality here, I think, is missing. Indeed, if a theory predicts novel phenomena, accommodation does not occur. So consider now that data, according to the relational view, are not simply given. They are not ready-made, but they are determined by operators, users, scientists in a specific context. And big data technologies have extremely strong predictive power thanks to technological development of neural networks. So anti-realists and hand of theorists, so to say, claim that given the relevant set of data, all the predictions can be thrown so that no theory can predict novel phenomena. Well, we can prepare artificially novel prediction, adding new data inside the theory, but in this case, data are already known. Instead, we can encounter serendipitous discoveries along with the scientific research processes while preparing data samples, while testing theories, while searching for experimental confirm. And take, for example, serendipity discoveries of penicillin by Fleming, the discovery of bacteria that cause stomach ulcers, and the isolation of vitamin C. In this example, according to Copeland, show that features of serendipity discoveries. And serendipities, according to her, is an emergent property of scientific discoveries. And this property describes an oblique relation between the outcome of a discovery process and the intentions that drove it forward, she writes in a paper. Serendipity conditions here seem at work in a phase behind the setting up of the theory, while intelligibility condition, according to direct model, the contextual model, have to be settled in the space of reasons of explanation and understanding. But if serendipity can be defined within a framework in which scientific activities are made also by novel prediction, then big data analysis can be considered as a good scientific practice. Okay, of course, under the relevant epistemic constraints, as we said, coherent with scientific research in which serendipitous discoveries have still a place. So to conclude, is novelty undermined by big data technologies? Are serendipitous discoveries undermined? Do data-centric sciences avoid novel prediction? I think not. And I claim that underdetermination of theory argument does not affect the understanding success of scientific research, and that big data technologies do not undermine novelty. So to conclude, we can reassume that from a set of data, we cannot infer a unique theory. Many strategies show that this is not the ultimate attack against scientific realism, like Alive, Sillos, and others authors say. Big data technologies, given a set of well-prepared data, have a strong predictive powers about the behavior of phenomena, and this is a well-known property of big data technologies, but theory's property to predict novel phenomena is irreducible to the predictive power of big data technologies. So the conclusion is that there is still place for serendipitous discoveries and novel predictions in data-centric sciences, and there is still place for a theory of data-centric scientific understanding compatible with serendipitous discoveries and novel predictions. So we are still on Mars by now, since many are the issues here to be studied, but the serendipity, discoveries, conditions, and condition of data-centric scientific understanding are relevant today to understand what are the scientific activities. And I think that the relational framework program proposed by Leonelli is a promising field also for these themes. Also for themes concerning, yes, scientific understanding, but also scientific realism. So the exploration continues, and I know that the other contributions here at the symposium will put the research further about these issues. So thank you all for your attention.